going to derive the equation of an ellipse whose center is not the origin, but to do so we have to first establish two relationships. I've already drawn the ellipse where the major axis is that green line, that horizontal green line across the center, where half of that line is A. And then I've drawn the minor axis, which is that yellow line, that vertical yellow line through the center, where half of the length of that minor axis is B. The fixed points are the two purple points to the left and right of the center, which is in pink, and the distance between each fixed point and the center is labeled C. Recall that our ellipse can be defined as the set of points for whom the sum of the distances to each of the fixed points remains unchanged. So let's say we have some points in the circumference, let's say maybe here, where we'll call the distances from that point to the fixed points, to the two purple points, D1 and D2. So we can go ahead and say that this distance here is D1, and well, this distance here is D2. If I go ahead and shift that point in the circumference, I'm going to put it instead on the major axis, so at the end of that horizontal line. Well, it means that my D1 and D2 become, say, this guy here. So that's now D1. And my D2 length will be, well, this guy. Maybe draw that over this guy here. Call that D2. And well, we could represent those lengths D1 and D2, or really the sum of those lengths D1 and D2 outside of the ellipse. So I'll just draw them over below, where that guy will be D1 and D2 would be this guy. And because of the symmetry of our ellipse, well, this length would be the same as that length, so that the sum of D1 and D2 will be the same as the length of the major axis, this guy going all the way across the center, whose length is 2A. So that's our first relationship. We could go ahead and say that, well, 2A, use the appropriate color, so 2A is equal to D1 plus D2. So that's the first relationship that we need to establish. The second relationship is, well, if we think about taking that point in the circumference, or considering the point in the circumference that's instead on the minor axis. So let's maybe just take these guys off so we have a little more room. So considering the point that's it here, and D1 would be this guy, D2 would be this guy. Well, by the symmetry, we know that D1 and D2 must be the same length. So I can use the first relationship that we've established and say that 2A is equal to, I'm going to go ahead and call D1 and D2 both just D, just to denote that they're the same length. So you could say that 2A is equal to D plus D. Of course, just in this specific case, not for all the points on the circumference, so just for the point on that minor axis. But that tells us then that, well, 2A is equal to 2D, and therefore A is equal to D. So it says for that particular point, the length of D, this line here, is going to be the same as the length of A. So I'm just going to go ahead and call that guy A. And then from there, all we want to kind of use is Pythagoras theorem. So we want to just go ahead and say that B squared plus C squared is A squared. And if we transpose over B squared, we get B squared is equal to A squared minus C squared. Those are the two relationships that we want to establish in order to derive the equation of our ellipse.